In previous videos, we talked about what probability is and what its fundamentals are. Previously, we were also introduced to the concept of random variables. In the context of probability and statistics, a random variable is a variable whose possible values are numerical outcomes of a random phenomenon. Let's just say, for instance, that x is a random variable, a discrete random variable to be exact. And this random variable is defined as a value you'd get after throwing a die once, and that variable can take on any value within a finite range, which in this case is between 1 and 6, inclusive of 1 and 6. Now, under conditions of randomness, at the time you throw the die, you wouldn't know which value you'll get until the die has stopped rolling. Now, assuming that we are throwing a fair die, meaning that the die was not manipulated in a way that a particular value is more likely to result, then all possible values of x have an equal chance of occurring. We also tackled probability distributions that are of importance in the field of medicine, namely the binomial, Poisson, and normal distributions. In the case of the binomial probability distribution, our random variable is discrete and has only two possible outcomes. Conventionally, we assign the value of 1 if the outcome of interest happened and 0 if it did not. Now, recall from earlier that the binomial probability distribution is given by this probability mass function, or PMF. Now, if we know the number of successes, or the number of times that x took on the value of 1 in a group of n number of observations, and if we know the probability of success, or p, which is either hypothesized or demonstrated in previous experiments, we will be able to derive the mean and the variance of this probability distribution. Now, with random variables that follow the Poisson distribution, such a random variable is defined as the discrete number of times an event of interest has occurred in a given time or space interval. Now, theoretically, this variable can take on any value between 0 and positive infinity. The Poisson probability distribution is given by this PMF. Now, recall that lambda is the mean number of events per interval in that particular experiment. And recall as well that it is also the same as the variance of this probability distribution. Lastly, we have the normal distribution wherein a continuous random variable has a frequency distribution curve that is bell-shaped. Now note that the peak of that curve corresponds to a particular value of the random variable which we call the mean. Now, since this value is in the middle of the bell-shaped curve, thus effectively dividing that curve into two mirror images, it is also called the median. And since this value is the one occurring most frequently, as can be seen by its correspondence to the peak of this bell-shaped curve, it is also called the mode. Now, for any continuous variable that follows the normal or Gaussian distribution, this is the respective probability distribution function, or PDF, where mu is a mean and sigma squared is the variance. Now let's say we want to conduct a study, and that study, for instance, involves measuring the blood levels of a particular antibody after being given an investigational vaccine. The random variable in this case is blood antibody level, which is a continuous variable. Now, for obvious reasons, we cannot measure the antibody levels of each and every healthy individual in the vast population at large that meets our study inclusion criteria, let alone administer the investigational vaccine to all of them. Instead, we get a representative sample of that population, which is smaller in terms of size and thus more manageable. This would then make it easier and more convenient for us as study investigators to conduct our antibody level measurements. Now, if we assume that these blood antibody values follow a normal distribution, or similarly, if we already have good knowledge beforehand, generally from previous studies or experiments, that antibody values indeed follow a normal distribution, we can use the means and variances of the blood antibody values we obtained or measured in our experiment to be able to derive information about the probability distribution of the sample of healthy participants that we have. Now, if we haven't violated any assumptions, we can be able to generalize our results to the whole population of healthy individuals. This is what is called as statistical inference. Here is the definition of statistical inference, which I lifted from the textbook by Daniel and Cross. So, statistical inference is the procedure by which we reach a conclusion about a population on the basis of information contained in a sample that has been drawn from the population. Now, whenever we perform what's called inferential statistical analysis, we actually infer or deduce properties about a certain population. Now, this analysis includes hypothesis testing and derivation of estimates, which I will talk about later. Let me supplement the definition of statistical inference with a schematic diagram of its concepts. We start off with identifying a population to which we are interested in generalizing the conclusions of our study or experiment. We then draw a representative sample from this population, and from that sample, we generate numerical data, which we then use to obtain pertinent statistics. We then use these statistics to estimate or test our hypothesis about the population parameters, which, as we already know, are unknown. After we've estimated these parameters or tested our hypothesis regarding them, we can then be able to draw conclusions about our target population. Now, assuming we've done everything properly in our study, the conclusions we obtain from our study have what's called external validity, meaning we can be able to generalize our results to the whole population. Now, while going through this schematic diagram, we encounter two important terms, statistic and parameter. This slide basically differentiates between these two terms. A parameter is a measure that describes the entire population. Because studying the entire population is generally not feasible and thus is seldom done, that measure remains largely unknown. A statistic, on the other hand, is an estimate of that population parameter. It is observed data based on a representative sample that was drawn randomly from the population and is therefore known. Take note that I use the word random. If sampling is done randomly, each member of that population has an equal chance of getting selected. Sampling that utilizes some form of random selection is what's called probability sampling, and there are various methods or ways of doing it depending on one's study design and objectives. The component of randomness is said to ensure representativeness of the sample that was drawn. Now, the value of a parameter is actually a constant, unlike its respective statistic, which could vary every time we repeat the same study, wherein we return our original sample back to the population and then again randomly draw a new sample from the same population. Each time we draw a new sample, we get a somewhat different measurement of the parameter estimate or statistic. We call this variation in the sample statistics value as sampling variation. Here is a short list showing the notations of common population parameters that are estimated, along with their corresponding sample statistics and their notations. We generally use Greek letters to denote parameters, while we use lowercase letters to denote the respective sample statistics. With some exceptions, however, like with the sample mean, wherein we use x bar instead. Sometimes uppercase letters are used to denote parameters, like in the case of proportions. The corresponding notation for the respective statistic, in this case, would be in lowercase, with a hat-shaped diacritic on top indicating that it is an estimate of the population parameter. So when we refer to the sample proportion, for example, we often say or refer to it as p hat. Let us now apply these notations to the schematic diagram from earlier. Here, we would like to make inferences about the population mean, denoted by Greek letter mu. The statistic we obtain from the sample is a sample mean, denoted by x bar. With that, we can now move on to estimation. Recall from earlier that statistical inference includes testing hypotheses and deriving estimates. Estimation, by definition, is the process of roughly calculating the value, number, quantity, or extent of something. In the biostatistical sense, estimation is the process by which a sample statistic is used to approximate the corresponding population parameter. There are generally two methods for estimation. The first being point estimation, wherein we estimate the population parameter with a single best guess number. Now, the point estimate does not really give us a complete picture because it doesn't really tell us how close or how far the estimate is likely to be to or from the population parameter. Hence, scientific journals would very rarely, if not never, report results using only point estimates. In all cases, a margin of error is incorporated in order to gauge the accuracy of the point estimate. The process by which we estimate this margin of error is called interval estimation. Hence, we estimate a range of values within which the true parameter lies with high probability. The interval estimates that are generated by this method of estimation are called confidence intervals, which are always reported alongside the point estimates. Now, when confidence intervals are wide, it generally means that there is a substantial amount of variability in the values of the sample statistic, and this translates to lower precision as far as the study is concerned. Now, this typically happens when the sample size is not large enough for a study to detect a difference, when in fact there is a difference. As the sample size increases, the study's precision improves, leading to lesser variability, which eventually results in narrower confidence intervals. Let us go back to this table from earlier. Recall that population parameters, which are constants, are the ones we estimate using inferential statistics, and the estimates that we get are the sample statistics, which are actually point estimates. Now, as I mentioned earlier, if we repeat the study or experiment many times, we will each time get a different point estimate, something we can largely blame on sampling variation. Now, keep this in mind as I talk about confidence intervals next. Confidence intervals are interval estimates we compute from observed data, which we obtain from the sample. Now, many references refer to confidence intervals as intervals that contain what are considered to be the most believable values for a population parameter. We can actually compute for the confidence interval using this general formula, wherein we add and subtract the product of the z-score or z-deviate and the standard error to and from the value of the sample statistic in order to get the upper and lower value of the interval. Now, since we want to construct a 95% confidence interval, the z-score we use is 1.96. I already talked about standardization of the normal distribution in a previous video where I discussed how to compute for the z-score. Now, choosing which confidence interval range to use is a subjective decision. It can depend largely on the nature of the study being conducted. With social sciences, for example, 85% confidence intervals are actually acceptable. In laboratory sciences, however, much higher levels, that is, at least 98 or 99%, are required, particularly when calibrating laboratory instruments. But as far as medicine goes, 95% confidence intervals are commonplace. Likewise, in the normal distribution video, I briefly discussed what standard error is. Now, the standard error is an estimate of how far the value of a sample statistic is likely to be from the population parameter, and this is equal to the standard deviation of that sample statistic divided by the square root of the sample size n. We will see later in this video that there are different ways of calculating the standard deviation and the standard error, depending on the sample statistic. Now, while reading journal articles, we often encounter the phrase 95% confidence interval. Many frequently think that this 95% represents the probability that a population parameter will fall between two set values. This is actually wrong. What this phrase actually means is that if 100 repeated samples were taken from a population, that is, the experiment or the study was performed repeatedly 100 times, and each time the 95% confidence interval was computed for each sample, 95 of the 100 generated confidence intervals would contain the population parameter. Now, similarly, it is also erroneous to state that a 95% confidence interval has a 0.95 probability of containing the population parameter, or that there is a 95% chance that the true population value is within this interval. What we can say instead is we are 95% confident that the true population value lies within the interval. The term confidence here does not refer to the interval itself, but rather to the process that generated it. Think of it more in the lines of being more self-assured that you have captured a population parameter, the unknown constant, within the upper and lower bounds of 95 out of 100 confidence intervals, since 100 repeated samples were drawn from the population. Of course, it will be too labor-intensive and very expensive if we repeated the same study 100 times, each with a different random sample. So one constructed confidence interval using the formula to estimate it should be enough, as long as no distribution assumptions were violated. Now, recall from a couple of slides back that I mentioned about a few different ways in which the standard error in the confidence interval estimation formula can be calculated, and that depends on what sample statistic we are dealing with. In this video, I'll be discussing how we perform interval estimation of population means and population proportions. Under interval estimation of population means, which I'll be talking about first, I'll also be discussing two cases. In the first case, the population variance is assumed to be known, and in the second case, the population variance is unknown. Before I start talking about interval estimation of population means, let's first do a quick review of what a sampling distribution is. Recall from earlier that the population parameter has a fixed or constant value, and this value is basically unknown. The sample statistic, on the other hand, has a value that varies every time a new sample is drawn randomly from the population. Since it is with the samples where we have actual numerical data or measurements, the sample statistic can be computed, and the values of this sample statistic are thus known to the researchers. Now, let's say a large number of samples are repeatedly drawn at random from this population. After we're done doing measurements on a randomly drawn sample, we return the sample back to the population before we perform the next random sampling to get our next sample. Now, with every sample of size n randomly drawn from the population, we get a different value for the sample statistic every time. Now, what if we constructed a histogram that graphs the different values of the statistic according to frequency? The resultant frequency distribution is what's called the sampling distribution. Let us illustrate this using an example. Let us define a group of 9 students enrolled in a biostatistics course as our population. The final grades of these 9 students are shown in the table. Now, just to give a little bit of background information on this type of grading system, a grade of 1.0 is the highest possible grade that a student can attain. A grade of 3 is the minimum passing grade. A grade of 4 is a conditional pass. And finally, a grade of 5.0 is an outright failure. Next, we compute for the population mean and variance, which are 3.0 and 1.333 respectively. Now, suppose we take a random sample of size 2 from the population, and these 2 students happen to be selected. We then get the x-bar, or the point estimate of the mean of that sample. Our x-bar in this case is equal to 2.5. Keep in mind, however, that we are basing our point estimate of the mean on just one sample of size 2. Now, what if we drew all the possible samples for this population without replacement? The phrase "without replacement" here means that we don't return a student back to the population after he or she has been randomly selected. After we've made measurements on a sample of size 2, that is, recorded these 2 students' grades, only then can we return them to the population before we make our next random selection. The number of possible samples we can draw from a population is determined by using the combination formula, which we've already learned in a previous video. So for this population, we can draw 36 possible samples of size 2. Now let us tabulate the computed sample means. What do you notice with these sample means? Now test yourself by pausing this video to briefly study this table. Now answer the question afterwards before proceeding to the next slide. If your answer is that the sample mean varies from sample to sample, then you are correct. Note that the values of these sample means range from 1.5 to 4.5. Now, because of this variation, we can actually consider the sample mean as a random variable. And with that, we can actually plot its frequency distribution, which we can call the sampling distribution of the mean. Now, the mean of this sampling distribution is denoted as mu sub x bar, while the standard deviation is denoted as sigma sub x bar. Now, if you do the math, you'd see that the mu sub x bar actually equals the population mean. Now, the sigma sub x bar, or the standard deviation of this sampling distribution, on the other hand, can be obtained by dividing the population standard deviation by the square root of the sample size, which is 2. Now, if you'll graph these sample means according to frequency in a histogram, you'll observe that the shape of the graph is bell-shaped or normal, or nearly so. Now, here's the frequency table of the sample means. The mean of the sample means is the same as the population mean, as what was mentioned earlier. And notice as well that the standard deviation of the sample means is actually smaller than that of the population. This is the histogram we will get if we graph the students' grades according to frequency. Notice that the distribution is somewhat shaped like a bell, and notice as well how the distribution is symmetrical to the mean, or mu sub x bar, that being 3.0. Now, having gone through that exercise, let me now discuss the properties of the sampling distribution of the sample mean. Let us consider a population and then consider a random variable x, whose mean we want to estimate. The properties of the sampling distribution of the sample mean would then be as follows. The sample means are normally distributed if the random variable x is also normally distributed. The mean of the sample means is equal to the population mean, and the standard deviation of the sample means which is often referred to as the standard error of the mean, is equal to the population standard deviation divided by the square root of sample size n. Now, you would recall in a previous video that I discussed a bit about the central limit theorem. According to this theorem, if we have a sufficiently large sample size from a population with a finite level of variance, the mean of all samples from the same population where the sufficiently large sample was drawn will be approximately equal to the mean of a population. Now, this theorem also basically states that the distribution of sample means approaches a normal distribution as the sample size increases. In order to demonstrate the central limit theorem, I will make use of the NHANES 2 data. Now, NHANES stands for the National Health and Nutrition Examination Survey. It is a large survey that was conducted nationwide in the United States by the National Center for Health Statistics between 1976 and 1980 in order to assess the health and nutrition status of American adults and children. Now, data from interviews and physical examinations, as well as laboratory data, were collected, and many variables were recorded in this huge survey. Now, according to the Center of Disease Control and Prevention, or the CDC, children and adults classified as living at or below the poverty line were sampled at considerably higher rates than their counterparts in the general population, because these groups of people were assumed to be at risk of having nutritional problems. Now, for those who use Stata as their statistical software, part of the NHANES 2 data is actually stored as an example dataset. For purposes of demonstration of the central limit theorem, I will likewise be using Stata and this example dataset. I will be looking at systolic blood pressure specifically. Now, here are the summary statistics for the data on systolic blood pressure. You'll notice that we have a pretty large number, which is 10,351. So we will define this large group as our population. So in this histogram, the participants were grouped according to 10 millimeter mercury increments in systolic blood pressure. As you see here, the shape of the graph is not symmetrical and is actually skewed to the right. Now, after issuing the command for the Shapiro-Wilk test, we learned that the systolic blood pressure data are not normally distributed, which is all right at this point since we are not performing any statistical tests for hypotheses that require the assumption of normality. In order to generate my sampling distributions, I'm going to make use of a statistical method called bootstrapping. I might eventually make a separate video on bootstrapping in the future to talk about it in more detail, but for our current purposes, we just need to know and understand that bootstrapping is basically a very useful resampling technique, and this resampling is done with replacement. Now, this technique is very useful in the sense that since researchers cannot keep on repeating the same experiment or study again and again because of financial or logistic reasons, amongst other reasons, they would rely instead on software to do repeated random sampling from the very large group of participants whose data these researchers already have, and make the necessary calculations for them. Now, resampling on the most part actually helps yield more informative, improved, and even unbiased estimates of population parameters. So earlier, we defined our population as the whole group of 10,351 respondents in NHANES 2, whose information is available to us via Stata. Now, using the bootstrapping function of Stata, the software will be repeatedly drawing a random sample of size 100 from this population of 10,351. I will be commanding Stata to repeat the process of random sampling by increasing amount of times. Note that our random variable of interest is systolic blood pressure, and for every repetition of the sampling process, the mean systolic blood pressure of that particular sample will be calculated and stored. In the next several slides, I will be showing various histograms wherein the sample means we obtained will be graphed according to frequency or number of times a particular sample mean was obtained. Now, with each histogram generated, I've included an overlaying normal distribution curve for our reference. Again, take note of the increasing number of repetitions performed, and take note as well of how the shape of the graph changes with increasing number of sampling repetitions. See how the shape of the graph approximates the normal distribution with increasing number of times random sampling was done? By doing 10,000 repetitions of drawing a sample of size 100, it's like we have a grand total of 1 million participants contributing to this last histogram. That is basically how the central limit theorem works. Now that I've finished tackling the theory behind interval estimation, let us now delve into the actual construction of confidence intervals. We begin by going back to this general formula for interval estimation. Take note of the z-scores or z-deviates corresponding to each confidence coefficient. As I mentioned previously, the interval estimation of mu involves two cases. The first case is that the population variance is assumed to be known, and the second case is that the population variance is unknown. Let's talk about the first case, where the population variance is known or assumed to be known. The first order of business is to standardize the sampling distribution of x bar, that is, we convert the sample mean to a z-score. In the normal distribution video, I initially introduced this formula for determining the z-score, but understand that x is no longer a random variable that is normally distributed, but rather it is x bar or the sample mean. And since we are now dealing with samples instead of populations, we no longer use the population standard deviation as a denominator, but rather the standard error, which is equal to the population standard deviation divided by the square root of the sample size. Now, after standardizing the sample mean, the z-score now becomes our normally distributed random variable, or more accurately, the random variable that has a standard normal distribution. Now, I'll place here the different z-scores or z-deviates along with their respective confidence coefficients. As I mentioned previously, using the 95% confidence interval is conventional and the most frequently used in medical research. Again, I urge you to be careful in interpreting the confidence interval. A 95% confidence interval of a population parameter does not mean that the interval has a probability of 0.95 that the true value of the parameter falls in the interval, or that there is a 95% chance that the true population value is within this interval. Recall from earlier that the correct way of interpreting a 95% confidence interval is by saying we are 95% confident that the true population value lies within the interval, that is, between an upper and a lower calculated value. Now, how do we tie this in with probability? The probability now becomes associated with the process that generated the interval. A really good way of looking at it is that a confidence interval either contains a population parameter or it does not. In the case of the 95% confidence interval, since the process was repeated, let's say 100 times, 95 of these generated confidence intervals contain the population parameter. Now that we're done with standardization of the sample means to the z-scores, which have a standard normal distribution, we can now regard the statement here as the probability that the z-score takes on a value between negative 1.96 and positive 1.96. And that probability is 0.95. So basically, 95% of the values of z are within these 2 points. Now recall from earlier that the formula for z is x bar minus mu over sigma divided by the square root of n. So we can actually make this substitution. Now by isolating mu between the inequality signs using algebra, we get this. It is important to remember that mu, that is the population mean, has a fixed constant value, which is however unknown. The one that is allowed to vary is the x bar, since x bar is now the random variable. That being said, a confidence interval can potentially have different values for its lower limit, which is given by this formula, and its upper limit, which is given by this formula. The way we interpret this now is that we are 95% confident that the true population mean lies within a particular lower limit value and an upper limit value. Let's have an example of how to construct a confidence interval. This is a word problem that I got from the textbook by Daniel and Cross. A physical therapist wished to estimate with 95% confidence the mean maximal strength of a particular muscle in a certain group of individuals. He is willing to assume that strength scores are approximately normally distributed with a variance of 144. A sample of 15 subjects who participated in the experiment yielded a mean of 84.3. Before we construct the confidence interval, we need to make sure that we have all the information that we need. Let's start off with solving for the lower limit. Now, just be careful with variance and standard deviation so that you don't confuse the two with each other. So our lower limit is calculated as 78.2, while our upper limit is 90.4. So with that, this is our interpretation. We are 95% confident that the true mean maximal strength is between 78.2 and 90.4. So in a nutshell, this is how you construct a confidence interval for a population mean when the variance is known. Unfortunately, it is rare that the true population variance or standard deviation is known. If this becomes the case, then the sample mean can no longer be standardized to z-scores, which we all know have a standard normal distribution. This is because we need a population standard deviation to standardize the sample means. What we can do instead is make the assumption that the sample variance, or S squared, is a good estimator of the population variance, and therefore we can use the sample standard deviation, or lowercase s, in the standardization formula in place of sigma. What we'll get as a result are not z-scores, but rather t-scores. And these t-scores in turn follow the t-distribution instead of the standard normal. Like with z-scores, we need a table to determine the t-scores that correspond to particular confidence intervals. But in contrast to z-scores at the same time, the t-scores that serve as limits of the confidence interval are dependent on two things. One, the so-called significance level, or alpha, and two, something that's called the degrees of freedom, which is very often abbreviated as df. Now, just to briefly describe these two concepts. The level of significance, or significance level, formally refers to the probability of rejecting the null hypothesis when it is true. We will learn more about this in better detail in the video on hypothesis testing, but for now it is already sufficient that you know that the significance level is designated by the Greek letter alpha. Hence, the significance level is oftentimes referred to as simply alpha. For now, it is also already sufficient for you to know that the alpha can be calculated by subtracting the confidence coefficient from 1. We then have these alphas corresponding to each confidence coefficient. Now, the degrees of freedom, on the other hand, is defined as the number of values involved in a calculation that are free to vary. Now, this definition may seem a bit abstract for those who are new to the concept, but for now, all we need to know is that the degrees of freedom, or df, is equal to the sample size minus 1. What is important, however, is to be able to distinguish if something is one-tailed or two-tailed. When we talk about hypothesis testing, we will be making use of statistical tests to see if, for example, a sample mean or sample proportion is significantly different from a hypothesized population mean or proportion. If we want to know if a sample statistic is either larger than or smaller than the hypothesized population parameter, then we need to conduct a one-tailed test of hypothesis. Here we keep alpha as is when using the t-distribution table. I will demonstrate how to go about with this with an example coming up shortly. On the other hand, if we only want to know if a sample statistic is significantly different from the hypothesized proportion parameter, then we conduct a two-tailed test of hypothesis. For the two-tailed t-test, we need to compute for 1 minus alpha over 2. If our alpha, for example, is 0.05, we need to look for the t-score we need under the 0.975 column in the t-distribution table, which I will demonstrate shortly. Now with that, we are ready to construct the confidence interval for the population mean given that the population variance is unknown. The general formula for obtaining the limits of this interval is the sample statistic plus minus the t-statistic, or t-score, corresponding to alpha and n-1 degrees of freedom, multiplied by the standard error. Now here are the formulas for determining the lower and upper limits of the confidence interval. Let's use an example to apply this. The average number of persons per household for the whole country based on the 1980 census result is 5.6. A random sample of 25 households in a survey done showed a mean household size of 5.2 persons with a standard deviation of 1.56. With this information, construct the confidence interval using alpha equals 0.10. As with the previous example, we need to first make sure that we have all the information we need. Now, in order to find the t-score we need to construct the confidence interval, we need to use the t-distribution table. But before that, we need to know first if the word problem is asking for something that is one-tailed or two-tailed. Now, since there was no directionality mentioned in the word problem, meaning The problem was not asking whether the sample mean is larger or smaller than the population mean. We actually considered this condition to be two-tailed. Now, here's a t-distribution table I got from the textbook by Daniel and Cross. We know that our alpha is 0.10, but since the condition is two-tailed, we need to solve for 1 minus alpha over 2. From that, we get 0.95, and the column that we need to concentrate on in the t-distribution table is this. Similarly, we know that we have 24 degrees of freedom. At the point where the row and column intersect, we get 1.7109. That is our t-score. Now, for purposes of computation, let's keep the t-score to just t decimal places. So the t-score that we've obtained now will be 1.711. With all of that out of the way, we can now proceed to constructing our 95% confidence interval. The lower limit of the confidence interval is 4.7, while the upper limit of the confidence interval is 5.7. Therefore, we are 95% confident that the true mean number of persons per household is between 4.7 and 5.7. Now, this marks the end of the discussion on interval estimation of population means. Let us now proceed to interval estimation of population proportions. Let's do a little review on qualitative variables. By now, we should already know that qualitative variables are not numerical in nature. If anything, they are generally for labeling purposes only. Now, since qualitative variables are not numerical and are not continuous data at that, many basic mathematical operations such as determining the mean and variance cannot be applied. Now, what we can do instead is to categorize the members of a particular population in two levels of these qualitative variables. Like for instance, a condition may have three categories, namely mild, moderate, and severe. Now, after we've categorized the population members, we can be able to determine the frequencies or counts for each category. Now, from these frequencies or counts, we could actually be able to compute for proportions for each category. Thus, for qualitative variables, proportions are the population parameters that researchers aim to estimate. Now, if you can still remember, outcome variables that are binary or dichotomous in nature follow the binomial probability distribution. It is either the study participant experienced the event or not. As such, the population can actually be thought of as being subdivided into either successes or failures. Note that these two groups are mutually exclusive events as far as the event, characteristic, or attribute of interest is concerned. Since it are the population proportions that are being estimated, the population successes and failures are thus denoted by uppercase P and Q respectively. Essentially, the probability of success is complementary to the probability of failure. Hence the mathematical expression of 1 minus P equals Q for the proportion of failures. Now, as with the sample means from earlier, let's construct the sampling distribution of sample proportions as well. Now, let's go back to the same biostatistics class of 9 students. Their final grades are as follows. Now, from this data, we can calculate the proportion of students whose grades are 2.0 or better, and that proportion is 0.33, which we will designate as our population proportion. Now, for those who may get a bit confused about this particular grading system, I've included a legend or guide in this slide. Now, suppose we take a random sample of size 2 from this population, and these two students happen to be selected. We then get the P or the point estimate of the proportion of students with grades 2.0 or better in that sample. Our P in this case is equal to 0.5. Keep in mind, however, that we are basing our point estimate of the proportion on just one sample of size 2. Now again, what if we drew all the possible samples for this population without replacement? The total number of possible samples we can draw from this population is 36, and we determine that using the combination formula. Let us then tabulate the computed sample proportions. As with the table of sample means from earlier, you may have noticed that the sample proportions vary from sample to sample. Now, because of this variation, we can actually consider the sample proportion as a random variable. And with that, we can actually plot its frequency distribution, which we call the sampling distribution of proportions. Now, the mean of the proportions of this sampling distribution is denoted as mu sub p, while the standard deviation is denoted as sigma sub p. Again, if you do the math, you see that mu sub p equals a population proportion. The sigma sub p, or the standard deviation of this sampling distribution, on the other hand, can be obtained by taking the square root of the product of the population proportion and its complementary proportion, all divided by the square root of n. If you'll graph these sample proportions according to frequency in a histogram, you'll observe that the shape of the graph is bell-shaped or normal, or nearly so. Now, here's the frequency table of the sample proportions. The mean of the sample proportions is the same as the population mean, as what was mentioned earlier. Notice as well that the standard deviation of the sample proportions is actually smaller than that of the population. Now, what I've been discussing in the past few slides actually describe the properties of the sampling distribution of the sample population, which I will again mention as summary in this slide. Now, let us consider a population and then consider a random variable x, whose proportion we want to estimate. Now, the properties of the sampling distribution of the sample proportion will then be as follows. The sample proportions are approximately normally distributed. That is, if the random variable x is also normally distributed. Now, the mean of the sample proportions is equal to the population proportion. And the standard deviation of the sample proportions, which is often called the standard error of the proportions, is equal to the population standard deviation divided by the square root of n. Now, whenever we want to estimate the population proportion, there is a minimum sample size requirement that we must compute. We need to make this computation in order to find out if our sample is sufficiently large. Because if the sample size is indeed large enough, the normal distribution can be approximated, and when that is the case, the properties that apply for normal distributions can also be applied to this large enough sample. Additionally, the distribution may also be transformed to the standard normal by converting or standardizing the sample proportions to z-scores. But how do we know if the size of our sample is large enough? Apparently, there are two conditions that a particular sample should satisfy in order to be deemed large enough. First, the product of the population proportion of successes and the sample size should be at least 5. Likewise, the product of the population proportion of failures and the sample size should be at least 5 as well. With that issue of sample size requirements out of the way, we can now begin discussion on estimation of the population proportion. Again, we go back to this general standardization formula. Our statistic this time is the proportion of subjects in the sample that have a particular event, characteristic, or attribute of interest. And we denote this as lowercase p. The uppercase p here is the proportion of individuals with that same event, characteristic, or attribute of interest in the population. The standard error is then given by the square root of the product of uppercase p and its complement divided by the square root of n, which is the size of the sample that was randomly drawn from the population. Now, we do the same thing that we did with interval estimation of the population mean, like what we did earlier in this video. We could actually substitute z with this formula that I just discussed in the previous slide. Now, we need to isolate the population proportion, or uppercase p, in the middle of this expression, that is, between the inequality signs. With a little bit of algebra, we get this. Thus, the respective formulas to compute for the lower and upper limits of the confidence interval are these. Since uppercase p, the population proportion, is oftentimes unknown, we substitute it for its point estimator lowercase p, which is the sample proportion, thus giving us this formula for constructing the confidence interval. We get the complement of the sample proportion, or lowercase q, by simply subtracting p from 1. Now let's crystallize these concepts that we just discussed using another word problem. In 2009, a social survey conducted in the US included 2,200 college students across 40 colleges and universities. Based on the survey results, 85% of the students reported feeling stressed on a daily basis. Give the point estimate of the parameter and compute and interpret the 99% confidence interval estimate of the parameter. Now, to be able to answer this question, we need to ask ourselves these additional questions. First, what is a variable of interest? What is a trait that these college students have that researchers are interested in? Now, basing on this word problem, the researchers appear to be interested in the proportion of college students who feel stressed on a daily basis, or else they wouldn't be asking that question in their survey. The variable here would then be the feeling of stress on a daily basis. Now, in this problem, this variable is dichotomous or binary. That is, Either you have the feeling of being stressed or you don't, which actually answers our next question. And we all know as well that there are the college students who possess this characteristic of interest. Now, lastly, what is the parameter being estimated? What we know is the sample proportion of college students who feel stressed on a daily basis. We use this sample statistic to estimate the true population proportion of college students who feel stressed on a daily basis. Now, let's go on to solve the word problem. Our point estimate here is 85%. That is, 85% of the 2,200 college students surveyed, or 1,870, reported a feeling of being stressed on a daily basis. Is our sample size large enough, though? Basing on the conditions that were laid out to us earlier, then yes, the sample size is actually more than enough. Let's now solve for the lower limit of the confidence interval. So, as what was mentioned earlier, oftentimes the population proportion is unknown, so we can actually substitute it with the sample proportion in the formula. Take note that since our desired confidence interval is the 99% confidence interval, we use a z-deviate of 2.58. We now end up with 0.8304 as the interval's lower limit. We then solve for the upper limit of that 99% confidence interval. That value is 0.8696. How do we interpret this then? Well, we say that we are 99% confident that the true proportion, implying the population proportion, of US college students who feel stressed on a daily basis is between 83.04% and 86.96%.